In this example, I'll pretend to be a reservoir engineer at a small operating company in the Bakken. A deal's come across my boss's desk to evaluate a new opportunity for acreage in Divide County, which is outside of the area that we normally operate. So I've been tasked with trying to find out as much as I can about that area in the shortest amount of time possible. To do that, I'll launch Production Workspace. Production Workspace now offers the ability to customize your display. I'm going to start by searching for wells in North Dakota and Divide County. Now we automatically zoom to the filter extents. The first thing I'm going to do is style my well spots. I'm going to style them by operator and size them. I'm just going to look at the top 5, and I will size them by 6-month oil. Turning on my legend, I see that major players in Divide County are SM Energy, Continental Resources, Samson, and Hunt. I want to find out how production has changed over time. And to do this, I'll launch a new chart, our vintage type curve. Maximize this view. And now with all of our charts, you can remove series by clicking the icons below. So this chart is telling me that 2015 had the highest peak rates for Divide County. So either better acreage is being drilled in 2015 or changes in engineering practices have led to higher production. I'm going to assume it's the latter, and based on that, I'm going to further refine my filter selection to only look at wells that had first production in 2015. I also want to get some feel for what the acreage quality is from a third party. So I'm going to add our drilling info's graded acreage layer to this map. I'll load the Bakken graded acreage oil map. And I'll change the transparency to 80%. So based on these results, I see that Divide County is sort of in F and G acreage, according to drilling info. So it's definitely away from the heart of the Bakken, but there definitely appears to be significant production possible in this area. My next question is, what reservoir is that production coming from? So one way to find the answer to that question is with the new grouping and aggregating tools. I'm going to group by operator, and then I will group by reservoir. I do this because different operators have different engineering methods, and so if I see consistent trends in reservoir across multiple operators, I can assume that that's because of the signal from the reservoir, higher reservoir quality. I can also see what aggregation is going to be applied to all of my data fields. These are the defaults. Again, I'm going to use 6-month oil, and here the default aggregation is average, which is what I'd like. So I'll apply those grouping choices. And now I'm looking at data grouped by operator and then by reservoir. I can look at this in a table view, or I can launch a new chart that we're offering, the comparative group chart. The comparative group chart is showing differences in average first 6-month oil. I see that Samson Resources Middle Bakken wells have the highest on average 6-month oil with 50,000 barrels. Continental Resources Middle Bakken wells are very close with 49,000 barrels on average. Then we see Samson Three Forks wells and then Continental Three Forks wells. So based on this, I'm going to say that Continental and Samson are approximately equal in terms of their engineering and operations. But the Middle Bakken wells tend to be a bit more productive than Three Forks wells in this county. Based on that, I'm going to further refine my filter selection. I'm going to come back to production. I'm going to filter by reservoir and look at Middle Bakken wells only. And now I'm working with 21 wells. Now I'll launch the decline curve tool. Automatically, a type curve is calculated from the time normalized monthly data for all of the checked wells. So to validate the data that's going into the type curve, I can click on each well individually to determine whether or not I want to exclude certain components from the type curve. For example, this well only has 2 months of data, so I'm going to remove it from the type curve. I can come back to the type curve and recalculate. You can see a very slight shift in the data. I can go through and now start fitting individual wells or the type curve. So the models that I choose are controlled here. If I select more than one model, the decline curve tool will automatically determine which model best fits the data and what the optimal parameters values are based on the combination of parameters that minimize the sum of squared errors. So this first Sioux Trail model, or first Sioux Trail well, is best fit by the power law model, and these are the optimal parameter values. You can step to the next one. This time series is best fit by the stretched exponential production decline model. And this third well is best fit with Duong. All of these optimal model identifications are being recorded in the table along with the best parameter values. I'll fit one more. This one's best fit by the logistic growth model. So interestingly, out of 4 wells, they've all been fit with different models. I can then come back to and fit the type curve. What best fits a type curve? This was the stretched exponential power decline. So let's just say I decide that I want to fit them all with ARP. I can do this by deselecting all of the boxes except for ARPs, and then going back and refitting each of these individual wells on the type curve. Oh, this one didn't get it set long. So now these have all been fit with ARPs, and I can compare them side by side, the parameter values. I can also then, if I decide that I want to go with ARPs, decide to forecast reserves. There's lots of settings that are possible here. I can, by default, I'll tell it to look for different segments, to look for outliers, and I'll forecast with 200 different simulations of an ARPS model that fits within the data, the observed data. So we'll start by simulating forecasting production for this well. We see the red line is the best fit that the model has identified, and then the different black lines are the P90, P70, P50 values. We can also switch this to a log scale. So we can see the probability forecasts on the time series plot, and we can also come down here and look at the probability plots. So this is the cumulative distribution representing the probabilistic reserves. So this is telling us, if we look at the 90th percentile probability, this is showing us that 90% of the simulations of this well produced at least 114,000 barrels of oil in, let's see, 48 months. We've modeled 36 months beyond the last observation, which was around 12 months out. We can see that 50% of the simulations of the same well produced about 123,000 barrels after 6 months, and only 10% of the simulations produced 132,000 barrels or more. So based on these probability values of the different simulations of the same well, these are all different simulations of the ARPS equation that fit within the bounds of the observations. We can identify what the most likely probability of the reserves is. So for some companies, they predict on the P50, but they hedge on the different percentile values. That's where some of this information can be obtained. This CDF is just the integral of this PDF of the reserves. We can come down here too and look at the optimal parameter, or these aren't the optimal parameters, the distribution of the parameter values. So in the 200 simulations, this is the distribution of the initial rate. So this was a nice Gaussian shape with the initial rate around 6,800 for the median. You can look at the initial decline and beta. So for this well, if this well was part of our potential acquisition, we could say that we have at least a 90% confidence that this well has reserves of at least 114,000 barrels. On our best estimate is that it has more than that, and our best hope estimate is that it would produce up to 132,000 barrels over 4 years. So a simulation like this can give you an idea of the potential for production in a given area when you don't really have any other information to work from.